Hello everyone, this is Chinnaiah Kalpana here. In this video, we're going to solve a differential equation using suitable integrating factors. So let's get going. Problem solve. Y cube minus 2yx square into dx plus 2xy square minus x cube into dy equal to 0. Given differential equation, y cube minus 2yx square into dx plus 2xy square minus x cube into dy equal to 0. Consider as equation number 1, which is in standard form, say mdx plus ndy equal to 0, right? Now we can write the above equation as y cube dx minus 2y x square dx plus 2x y square dy minus x cube dy equal to 0, right? Now take y square common from these two terms and x square common from these two terms. You'll get, just write first term, third term firstly. Now the remaining terms. Okay. Now we can take y square common from these two terms. We'll get y square of y dx plus 2x dy, right? And take x square common from the next two terms. You'll get plus of minus, you're taking x square common, right? You'll get x square times minus 2y dx minus x dy equal to 0. Now we can write this equation as x power 0 y square. Okay, here you are having just y square, right? Y square is nothing but, you can just write y square as 1 into y square, and you can replace 1 by x power 0 since x power 0 is 1, right? So you'll get x power 0 y square into y dx plus 2x dy plus, here you're having x square, right? And you don't have any y terms, so you can write x square as x square into 1 and replace this 1 by y power 0. Okay, you'll get x square y power 0 into minus 2y dx minus x dy equal to 0. Consider as equation number 2, which is of the form x power a y power b into my dx plus nx dy plus, already we have used a b, right? Next let's take c and d. X power c y power d into, here we have taken m and n, right? Now we'll take p and q, py dx plus qx dy equal to 0. Okay, now by comparing these two equations, you'll get the values of constants. A equal to 0, b equal to 2, m equal to 1, n equal to 2, c equal to 2, d equal to 0, p equal to minus 2, q equal to minus 1, which are constants. Okay, since the given equation is written in this form, so here our integrating factor will be x power alpha and y power beta, or x power h, y power some k. Okay, here we need to find alpha and beta. We'll see that later. So you can ask why we are taking x square common from these two terms. If you observe the first term, you're having y cube dx and you don't have y squares in these two terms, right? So we have only choice. Here only you're having y square, right? So you can take y square common from these two terms. So by taking y square common, you'll get y dx plus 2x dy, something y dx plus x dy form, or you'll get an expression of mydx plus nxdy form. Okay, likewise here also, see you're having x cube dy here and you don't have any x cube or x square in these terms, so you have only x square in the quotient of dx, right? So we can take x square common, so that by taking x square you'll get something pydx plus qxdy form. I mean, you'll get an expression of pydx plus qxdy form. Okay, and here we are given a differential equation of mdx plus ndy equal to 0 form, which is not exact. Okay, that I'll show you later, which is exact or not. Firstly, you have to check whether the given differential equation is exact or not. Since the given equation is of the form mdx plus ndy equal to 0, which is not exact. Okay, I'll show this later, finally, after finishing the problem. Now, since the given equation can be written in x power a y power b of mydx plus nxdy plus x power c y power d of pydx plus qxdy equal to 0 form, so here x power alpha y power beta will be the integrating factor. Let x power alpha y power beta be the integrating factor. Multiply 1 by integrating factor, or multiplying 1 by integrating factor, we have to make the given equation to exact, right? So we know that by multiplying the given differential equation with some integrating factor, the equation becomes exact, right? X power alpha y power beta into the given equation, y cube minus 2y x square into dx plus 2x y square minus x cube into dy equal to 0. Then we'll get x power alpha y power beta into y cube minus 2y x square into dx plus x power alpha y power beta into 2x y square minus x cube dy equal to 0. This gives us x power alpha y power beta into y cube minus 2 x power alpha x square y power beta into y into dx plus 2 x power alpha x y power beta y square minus x power alpha x cube y power beta into dy equal to 0. This gives us x power alpha y power beta into y cube can be written as y power beta plus 3. Just add the powers. Minus 2 into x power alpha into x square can be written as x power alpha plus 2 by adding powers. And y power beta into y is y power beta plus 1 into dx plus 2 into x power alpha into x is x power alpha plus 1, y power beta into y square is y power beta plus 2, minus x power alpha into x cube is x power alpha plus 3 into y power beta into dy equal to 0, right? Now consider this equation as equation number 3. Okay. Equation 3 is exact if you can consider it as mdx plus ndy equal to 0, say, or m1 dx plus n1 dy equal to 0, where m1 is this one, that is the coefficient of dx, and n1 is coefficient of dy. If dou, that is partial derivative of m1 with respect to y equal to partial derivative of n1 with respect to x. Okay. Then dou by dou y of m1 x power alpha y power beta plus 3, that is minus 2x alpha plus 2 y power beta plus 1 equal to dou by dou x of n1 2x power alpha plus 1 y power beta plus 2 minus x power alpha plus 3 y power beta, right? Let's find the partial derivatives. Is equals to, see here it's a partial derivative of y, right? So x will be constant. Here x power alpha 2 x power alpha plus 2 is constant, right? So we'll write this as, I'll go with 2 steps, okay? You can skip this step. Partial derivative of first term with respect to y minus partial derivative of second term with respect to y. Equal to, here it is a partial derivative, we need to find partial derivative of this term with respect to x. So we can write this as dou by dou x of first term. Here we need to find partial derivative of these terms with respect to x. So here y is treated as constant. Here 2 and y power beta plus 2 is constant, and in the second term y power beta is constant, okay? Now let's write the constants outside the brackets. So here x power alpha is constant, so we can write the first term as x power alpha into partial derivative, x power alpha into partial derivative of y power beta plus 3, okay, minus, here 2 and x power alpha plus 2 is constant, so we can write this as 2 x power alpha plus 2 into partial derivative of y power beta plus 1 equal to here 2 and y power beta plus 2 is constant, so we can write this as 2 y power beta plus 2 into partial derivative of x power alpha plus 1 minus, here y power beta is constant, so we can write the last term as y power beta into partial derivative of x power alpha plus 3. This gives us x power alpha into partial derivative of y power beta plus 3 with respect to y is beta plus 3 into y power beta plus 3 minus 1, right? Minus 2x power alpha plus 2 into partial derivative of y power beta plus 1 with respect to y is beta plus 1 into y power beta plus 1 minus 1 equal to 2 y power beta plus 2 into partial derivative of x power alpha plus 1 with respect to x is alpha plus 1 into x power alpha plus 1 minus 1 minus y power beta into partial derivative of x power alpha plus 3 is alpha plus 3 into x to the power alpha plus 3 minus 1. Okay, this gives us x power alpha or beta plus 3 into x power alpha y power beta plus 3 minus 1 is beta plus 2. Okay, minus 2 beta plus 3, it's 1, right? Sorry, beta plus 1 into x power alpha plus 2 into y power beta plus 1 minus 1 is beta equal to 2 alpha plus 1 into x power alpha plus 1 minus 1 is x power alpha into y power beta plus 2 minus x plus 3, sorry, it's alpha plus 3 into x power alpha plus 3 minus 1 is alpha plus 2. We'll get alpha plus 2 into y power beta. In the next step, we'll equate the quotient of x power alpha y power beta plus 2 and we'll equate the quotient of x power alpha plus 2 y power beta. Equating quotient of x power alpha y power beta plus 2, which gives us beta plus 3 equal to 2 times alpha plus 1, or we can write this as beta plus 3 equal to 2 alpha plus 2 or 2 alpha plus 2 equal to beta plus 3. Now bring this beta to LHS, take this 2 to RHS. Okay, we'll bring beta to LHS and take this 2 to RHS. We'll get 2 alpha minus beta equal to 3 minus 2, which gives us 2 alpha minus beta equal to 3 minus 2, 1. Okay, consider it as some equation number A for our convenience. Now equating quotient of x power alpha plus 2 and y power beta. We'll get minus 2 times beta plus 1 equal to minus of alpha plus 3, which gives us 2 times beta plus 1 equal to alpha plus 3 or 2 beta plus 2 equal to alpha plus 3 or alpha plus 3 equal to 2 beta plus 2. Now bring this 2 beta to LHS and take this 3 to RHS. You'll get alpha minus 2 beta equal to 2 minus 3, which gives us alpha minus 2 beta equal to minus 1. Consider it as equation number B. Now by solving equation A and equation B, we'll get alpha and beta, and finally we'll put that alpha and beta in integrating factor and we'll multiply the given equation by the original integrating factor, that is by finding, after finding alpha and beta. Okay, So we have equation A and equation B. In equation A you are having 2 alpha. In equation B we are having alpha, right? In order to cancel the terms involving alpha by solving A and B, we need a 2 here. So what we'll do is we'll just multiply equation B by 2. Okay, we'll multiply equation B by 2. Now solving A and B. Equation A, 2 alpha minus beta equal to 1. Equation B, just multiply equation B by 2, you'll get 2 alpha minus 2 into 2 beta is 4 beta equal to minus 1 into 2 minus 2. Now change the signs. Here plus 2 alpha minus 2 alpha gets cancelled. Minus beta plus 4 beta equal to 1 plus 2, 3. You can just directly write minus beta plus 4 beta is plus 3 beta. You'll get 3 beta equal to 3. From this you'll get beta equal to 3 by 3, which is 1. Therefore, beta equal to 1. We have equation A, which is 2 alpha minus beta equal to 1. Now substitute beta, or take first, you can take beta to RHS. Just take beta to RHS, you'll get 2 alpha equal to 1 plus beta. Now you can replace beta by 1 since beta equal to 1, right? This gives us 2 alpha equal to 2, right? From this we'll get alpha equal to 2 by 2, which is 1. Therefore, alpha equal to 1. So we got the values of alpha and beta. Alpha equal to 1, beta equal to 1. Now coming to integrating factor. Integrating factor becomes x power alpha y power beta equal to x power alpha 1 beta 1, which is equals to x into y, that is xy. Therefore, integrating factor is xy. Now let's multiply this integrating factor to equation 1 so that equation 1 becomes xz. Okay, let's try. Now multiplying 1 by xy, which is an integrating factor. Okay, xy into the given equation, y cube minus 2y x square dx plus 2x y square minus x cube into dy equal to 0, which gives us xy into y cube minus 2y x square dx plus xy into 2x y square minus x cube into dy. Then x into y cube into y power 4 minus 2 x into x square x cube y into y square into dx plus 2 x into x square y into y into y square y cube minus x into x cube x power 4 into y into dy. Consider as equation number 4. See, this is also in mdx plus ndy form. So let's consider it as m2 dx plus n2 dy equal to 0 form. Okay, where m2 is x y power 4 minus 2x cube y square, and n2 is 2x square y cube minus x power 4 y. Now let's see whether equation 4 is exact or not. Okay, equation 4 is exact if partial derivative of m2 with respect to y equal to partial derivative of n2 with respect to x. Let's check that now. Partial derivative of m2 with respect to y equal to dou by dou y of xy power 4 minus 2x cube y square. So it's a partial derivative of y, so x is treated as constant. We can write this as dou by dou y of first term minus dou by dou y of second term. Here x is constant, so we can write this as x into dou by dou y of y power 4 minus, here 2x cube is constant, so we can write it as 2x cube into dou by dou y of y square, which gives us x into partial derivative of y power 4 with respect to y is 4y cube minus 2x cube into partial derivative of y square with respect to y is 2y, right, which gives us 4xy cube minus 2 2s are 4 x cube y. Therefore, partial derivative of m2 with respect to y is 4xy cube minus 4x cube y. Okay, let's now find partial derivative of n2 with respect to x. Dou by dou x of n2 2x square y cube minus x power 4 y. Here we are finding partial derivative of x, n2 with respect to x. So here y is treated as constant. Partial derivative of first term minus partial derivative of second term is equals to, here 2y cube is constant, so we can write the first term as 2y cube into dou by dou x of x square minus, here y is constant, so we can write the second term as y into partial derivative of x power 4 is equals to 2y cube into partial derivative of x square with respect to x is 2x minus y into partial derivative of x power 4 with respect to x is 4x cube, which gives us 2 2s are 4 xy cube minus 4x cube y, right? Therefore, partial derivative of n2 with respect to x is 4xy cube minus 4x cube y, right? See, we got dou m2 by dou y equal to dou n2 by dou x equal to 4xy cube minus 4x cube y, right? Therefore, equation 4 is exact. Now let's find the solution to exact equation, that is equation 4, which will be the general solution to equation 1 or the given equation. The general solution is given by integral m2 dx, treating y as constant, plus integral n2 terms of n2 free from x into dy equal to c. Okay, now let's find integral m2 dx, I mean first integral and second integral separately. m2 x y power 4 minus 2x cube y square into dx. Here y has to be treated as constant, so y power 4 and y square are constants, 2 is also constant, so we can write this integral as y power 4 integral x dx, or I'll write one more step, okay, integral x y power 4 dx minus integral 2 x cube y square dx. Now I'll take the constant outside the integral. Y power 4 integral x dx minus 2y square integral x cube dx, which gives us y power 4 into integral x dx is x square by 2 minus 2y square into integral x cube dx is x power 4 by 4. To 2 is equals to x square y power 4, x square y power 4 by 2 minus x power 4 y square by 2, or just take the LCM of these two denominators, we'll get 2, right, which gives us x square y power 4 minus x power 4 y square by 2. Therefore, integral m2 dx is x square y power 4 minus x power 4 y square by 2. Now coming to the second one, integral n2 terms of n2 free from x into dy. Just observe n2. Do we have any terms which are free from x? No. Here we are having, in the first term we are having x square, and in the second term we are having x power 4. So there is no such n2 which is free from, I mean there is no term in n2 which is free from x. So this is equals to 0. Integral n2 terms of n2 free from x into dy equal to 0. Now coming to the general solution. Therefore, the general solution is result obtained from the first integral is x square y power 4 minus x power 4 y square by 2 plus result obtained from the second term is 0 equal to c, or we can write this as x square y power 4 minus x power 4 y square by 2 equal to c, or x square y power 4 minus x power 4 y square equal to 2c. Okay. Since c is arbitrary constant, 2 is constant, so we can write 2c as some c, right? Then this gives us x square y power 4 minus x power 4 y square equal to c, which is the required solution to our problem. This completes the problem. Or we can write this as you can take x square y square common from these two terms, right? You'll get x square y square times y square minus x square equal to c. Therefore, x square y power 4 minus x power 4 y square equal to c, or x square y square of y square minus x square equal to c is the required solution. Now we have completed the problem. Let's now check whether the given differential equation is exact or not, right? We have skipped that, right? At the beginning we have skipped to show that the given differential equation is non-exact. So now we are going to prove that. As I said earlier, the given differential equation is in mdx+ndy equal to 0 form. That is the standard form, where m is y cube minus 2yx square and n is 2xy square minus x cube, right? So equation 1 is exact if dou m by dou y equal to dou n by dou x, right? Let's now find partial derivative of m with respect to y and partial derivative of n with respect to x. Partial derivative of m with respect to y is (3y square). Since it is partial derivative with respect to y, so x is treated as constant, minus 2x square into partial derivative of y with respect to y is 1, which is equals to 3y square minus 2x square. Let's now find the partial derivative of n with respect to x. Since it is a partial derivative of n with respect to x, so we'll treat y as constant. You'll get 2y square into derivative of x with respect to x is 1 minus partial derivative of x cube with respect to x is 3x square, which gives us 2y square minus 3x square. So by observing these two, we can say that partial derivative of m with respect to y is not equal to partial derivative of n with respect to x, right? So 1 is not exact, right? So we have seen a problem from differential equation in this video whose integrating factor is x power alpha y power beta or x power h into y power k. I hope you'll understand. We'll see you in the next video. Until then, bye bye.